Mast bumping? Sure, we went over that when I got checked out in the Huey. You can get it during slope landings.
Sure, I know about it. Only I call it excessive flapping. It's most likely to happen after I shut down the engine and a wind gust causes the rotor to teeter excessively.
Actually, it's in-flight mast bumping that we've all got to avoid. Mast bumping caused by near zero-G flight, out-of-CG conditions, or abrupt control movements.
One of the functions of the Army Agency for Aviation Safety is to analyze aircraft accidents to determine causes and then make recommendations to prevent similar accidents in the future. A study of Army mishap experience involving UH-1 and AH-1 helicopters shows that mast bumping in flight can cause mast failure and complete rotor separation, producing catastrophic accidents. Analysis reveals that mast bumping accidents can be prevented provided you, as a helicopter pilot, understand mast bumping and know what to do to avoid it. This film will first show what mast bumping is in the Huey and Cobra, then show the in-flight conditions which can precede mast bumping, and last, and by far the most important, how you can avoid mast bumping. It may be necessary to view the film more than once, for some of the required corrective actions are counterinstinctive. It is absolutely essential that you completely understand what causes mast bumping and what to do to avoid it.
In the Huey and Cobra, inappropriate pilot response to low-G maneuvers or mechanical failure can lead to mast bumping and possible in-flight separation. As an Army helicopter pilot, you must understand the operational characteristics of the UH-1 and AH-1 and know how to handle these aircraft to avoid mast bumping. To help you understand why mast bumping occurs and what you can do to avoid it, we'll first review some of the basics of the rotor and the control systems and the aerodynamics that lead to mast bumping. We'll then discuss these factors in terms of operational flight maneuvers and describe what you, as a pilot, must do to prevent the onset of mast bumping. First, mast bumping is the result of excessive rotor flapping. Flapping is the characteristic of a rotor blade to move up and down during rotation. Flapping is common to all helicopter rotor systems and is normal and expected. The rotors of the UH-1 and AH-1 use a seesaw action about a hinge pin to accommodate flapping. To prevent the blades from contacting the tail boom or other structure during normal starts and stops, the interior of the hub is fitted with static stops. These are contoured to limit the amount of blade flap, and sufficient clearance is provided between hub and static stops for all normal maneuvers. On the UH-1, the maximum flapping angle is just over 11.5 degrees. On the AH-1, it's 12.5 degrees. If flapping exceeds these values, the stops will bump the mast. It is the violent contact between the static stops and the mast during flight that causes mast separation, and this you must avoid at all costs. A turning rotor has a constant flapping pattern. Maximum flapping up will always be opposed by maximum flapping down, 180 degrees later. At normal operating speeds, the individual blades blur into a disc shape. When this rotor disc is not at a right angle to the mast, flapping is occurring. Now let's examine how flapping can occur as a result of pilot control inputs. The cyclic control stick transmits inputs through the swash plate, changing blade pitch. The rotor disc will flap in the direction the stick is moved. So, cyclic stick movement produces rotor flap. The pilot controls the position of the rotor disc. In flight, when the rotor disc tilts, the aircraft responds by moving in the same direction. In this way, the pilot controls the helicopter. Mast bumping is directly related to how much you as a pilot allow the blade system to flap. And to understand this better, we have to dig a little deeper. In straight and level flight, blade flapping is minimal and difficult to see in real time or even, for that matter, in slow motion. Flapping angles of less than 2 degrees are expected under usual flight conditions. You can expect flapping angles to increase by 1 or 2 degrees with high forward speeds, at low rotor RPM, at high density altitudes, or at high gross weights. You can also expect increased flapping angles during turbulence. Aircraft maneuvering can also induce large flapping angles. For example, side slips and low speed flight at extreme CG positions. The risk of excessive flapping and possible mast bumping increases when you allow the aircraft to approach low G conditions. And that's what we really want to talk about. Let's see what happens when a pilot encounters a ridge line or a tree line, executes a cyclic climb, and then noses over using abrupt forward cyclic. In this maneuver, he has deliberately given up G loading on the rotor disc by changing rapidly from upward to downward flight and is approaching 0 G. Higher speeds aggravate the situation. The combination of down collective and low G means that lift, and therefore thrust, has essentially disappeared. Let's look at the situation from aft along the roll axis. Absence of thrust means there is no lateral cyclic control, so cyclic movement cannot change fuselage position. The aircraft does not respond because the pilot has given up G loading on the rotor disc. The thrust of the tail rotor, acting above the helicopter's center of gravity, starts the fuselage rolling to the right. Seeing this, the pilot wants to counter the roll, normally the right thing to do. Tail rotor thrust acting above the aircraft's CG will cause right roll rate to build up rapidly. Alarmed by the excessive roll rate, the pilot abruptly applies left cyclic. The rotor disc tilts in the direction commanded by the pilot. The pilot still has rotor control, but he is controlling an unloaded rotor. That is, a rotor that is not producing thrust. Although he still has fore and aft control, he has lost roll control of the helicopter. Flapping increases drastically. The rotor hub strikes the mast violently, on one side, then the other, and the mast may separate. Let's go back to the point where the roll started to see what the pilot should have done. As we saw before, as the aircraft rolled, lateral cyclic inputs could not develop thrust because there was no change in angle of attack of the rotor system with respect to the relative wind. Consequently, there was no positive lateral cyclic control. In contrast, let's look at the situation in the pitch axis. Similar to the roll case, aft cyclic inputs cause the rotor disc to move. But in this case, the disc movement changes the disc angle of attack. Aft cyclic realigns the rotor and thrust is restored. The nose pitches up. And with thrust once again available, the pilot is able to counteract the roll. Let's make sure we all understand what the pilot should have done during the nose-over maneuver. He could have avoided the low G condition by using more gradual forward cyclic. The rate and extent of cyclic motion should be adjusted to keep the rotor loaded at all times. As a pilot, you clearly minimize the likelihood of mast bumping by staying above 1/2 G at all times, thereby preventing approach to low G and the right roll tendency. If the rotor becomes unloaded during low G, it is absolutely essential to recover thrust first by smoothly moving the cyclic stick aft. Once thrust is restored, left cyclic will then return the aircraft to the normal flight attitude. The basic lesson here is that the pilot contributes to the potential of mast bumping in the low G environment, because any pilot's instinctive reaction when a roll begins is to correct it with lateral cyclic. And the greater the roll rate, the more abrupt the control movement is likely to be. Severe flight attitudes seem to call for severe control inputs. Yet it's the severity of these inputs that can produce worse problems. If you encounter low G conditions, remember, avoid abrupt, large magnitude control inputs. Smooth, gradual control movements are essential. First, aft cyclic to restore the thrust. Then and only then, left cyclic to correct for right roll. You may also encounter low G conditions during mast unmasking maneuvers or steep descending nose-low turns. If these maneuvers are performed with abrupt, uncoordinated, or cross-control inputs, the rapid changes from upward to downward flight may unload the rotor and induce mast bumping. The risk of mast bumping also increases in turbulence when sudden upward and downward drafts can unload the rotor and get you into low G conditions. If that should happen, you must resist the instinctive urge to counteract unusual aircraft attitudes with hard lateral cyclic and pedal inputs. You must first reload the rotor by moving the cyclic stick aft. Then, once normal G conditions have been reestablished, normal control will return. But how about another possible cause of mast bumping? Engine failure. What should the pilot do to control this situation? Again, let's get back to some basics so that we can understand what happens. First, under normal conditions, and then when the engine fails. The actions we'll be talking about are complex, so it helps to imagine there's a camera along each axis, together with one behind the cockpit. At this moment, let's say the helicopter is flying in its normal cruise attitude. That means the longitudinal axis, and therefore the nose, is pitched down slightly, and the rotor disc is tilted slightly forward. From aft, the rotor disc is tilted slightly to the left to counter the rightward thrust of the tail rotor. The roll axis is located below the tail rotor thrust axis. From above, the main rotor rotation is counterclockwise. The resulting torque would force the nose to the right if it were not for the anti-torque thrust of the tail rotor and vertical fin. The airflow over the main rotor and fuselage would tend to raise the tail if it were not for the synchronized elevator. In normal flight, then, all forces are balanced and the helicopter is in equilibrium. From the cockpit point of view, the horizon is horizontal. Most engine failures do not result in mast bumping, but it can happen if the pilot fails to take appropriate action. Let's say the aircraft is in normal flight, all forces balanced. Then the engine fails suddenly. As the engine stops, the rotor RPM and airspeed both begin to decay, with some loss in altitude. Because the engine is no longer driving the main rotor and RPM is decaying, the torque about the mast that had been opposed by the tail rotor and fin is diminishing. So now, the tail rotor and fin, continuing to thrust to the right, causes the nose to yaw left. Interaction of the relative wind with the yawed helicopter and main rotor causes the aircraft to roll left. The pilot may see this as a nose-down tendency. The change in attitude has been abrupt and is continuing at an alarming rate. The pilot, responding to what he perceives as a nose-down, left yaw situation, reacts abruptly, but in the wrong manner for the case at hand. Right aft cyclic and right pedal, but he fails to lower collective. Right aft cyclic immediately tilts the rotor disc right and aft, and failure to lower collective results in decaying rotor RPM. This will result in larger flapping angles. Mast bumping may then occur. The remedy? Work on the primary problem, not the symptom. In this case, the symptom is the roll. The problem is power loss. So, when a loss of power is detected, you need to decrease the collective pitch to avoid a reduction in rotor RPM and apply sufficient right pedal to maintain a constant heading and enter auto rotation. But now, suppose you lose the tail rotor. In this case, the situation is practically a mirror image of engine failure. But it's further complicated because you've lost one of your primary control forces, tail rotor thrust. Let's see what happens. The instant the tail rotor fails, anti-torque thrust goes to zero and only the fin remains to resist the torque about the main mast. The reduction in anti-torque thrust induces right yaw and left roll. Yaw attitude now exposes flat areas on the left side of the aircraft and the nose to the relative wind. This induces a roll to the left, aggravated by the absence of tail rotor thrust above the longitudinal axis that could have countered a roll in this direction. Almost instantly, the aircraft can yaw right, roll left, and pitch down. In this example, the pilot fails to lower collective to reduce the torque that is causing his aircraft to yaw. Instead, he moves the cyclic aft right again, working on the wrong thing, the symptoms, and not the problem. With the fuselage already rolling left, right cyclic tilts the rotor disc toward the fuselage and mast bumping threatens. The problem in this case is the torque tending to yaw the aircraft. The proper procedure in the event of tail rotor loss must be immediate reduction in power. You should then enter auto rotation. Power reduction will reduce the yawing tendency and therefore allow more time to correct the roll situation smoothly. With reduced throttle and collective, keep an airspeed slightly above the normal autorotative glide speed. You can experiment with gentle throttle and pitch application to see if some degree of powered flight can be resumed. But if any adverse yawing is experienced, re-enter auto rotation, continue descent, and land. For the past few minutes, we have reviewed some factors which are critical to your operation of the UH-1 and the AH-1 aircraft. We have reviewed mast bumping, what causes it, and how to prevent it. We saw that mast bumping is the result of excessive rotor flapping, and that the problem is directly related to how much you as a pilot allow the blade system to flap. We pointed out that the cyclic stick and swash plate make it possible for the pilot to control the tilt of the rotor disc. We saw that blade flapping is minimal in straight and level flight, less than 2 degrees under usual conditions. We then discussed how excessive flapping and possible mast bumping may be caused by aircraft maneuvering, particularly when you allow the aircraft to approach low G conditions. We explained that the rotor becomes unloaded during low G. We saw that the crucial issue was the loss of rotor thrust, because it's those times when the rotor is not producing thrust that lateral cyclic movement of the unloaded rotor disc will not only fail to control the helicopter, but can result in mast bumping. We then explained how to counteract the effects of low G by recovering rotor thrust, first by smoothly moving the cyclic aft, then and only then left cyclic to correct for right roll. We also examined how engine failure or loss of tail rotor can cause mast bumping and the corrective actions the pilot should take, explaining that in the case of a loss of power, you should decrease collective and apply right pedal immediately to avoid a reduction in rotor RPM. Then enter auto rotation. Now, if the tail rotor fails, immediately reduce power, then enter auto rotation. The basic lesson here, and the single most important message that should have come through, is that you as a pilot can prevent mast bumping by the way you handle the aircraft. It is absolutely essential that your control inputs be smooth and gradual, even in difficult situations such as low G, because it is abrupt and full range control inputs combined with mechanical factors that cause mast bumping.
It is crucial that you understand the operational characteristics of the UH-1 and AH-1 rotor systems and how normal blade flapping limits can be exceeded and result in mast bumping and possible mast separation. Again, I urge that this film be rerun until each and every one of you is completely confident that you know what to do to avoid mast bumping. Mast bumping is real, but it can and must be prevented. It is vital that you understand the part you play.